If you've ever watched a hydrogen company presentation and seen one slide claiming 72% efficiency, and then another company claiming 60% efficiency for what appears to be a similar electrolyzer, you might assume one of them has superior technology. You might assume one stack design is more advanced. You might assume one manufacturer has achieved a breakthrough in membranes, catalysts, or current density. But in many cases, the difference has nothing to do with engineering at all. It has to do with accounting. And specifically, it has to do with something called higher heating value versus lower heating value. Today, we're unpacking the 15% hydrogen efficiency trick that almost no one explains clearly, even though it directly affects investment decisions, industrial fuel switching, hydrogen pricing, and even carbon policy benchmarks. Let's begin with fundamentals. Look at Image 1. Image 1 shows the thermodynamic energy content of hydrogen under two different definitions. The higher heating value, or HHV, of hydrogen is 141.8 megajoules per kilogram. In electrical terms, that equals 39.4 kilowatt hours per kilogram. The lower heating value, or LHV, is 120 megajoules per kilogram, which equals 33.3 kilowatt hours per kilogram. The difference between these two values is 21.8 megajoules per kilogram. That number is not arbitrary. It represents the latent heat of vaporization of the water formed when hydrogen is combusted. When hydrogen burns in oxygen, the reaction forms water. That water leaves the reaction as vapor. If you cool that vapor back into liquid form, it releases heat. HHV assumes that this condensation heat is fully recovered. LHV assumes it is not recovered. So the difference between HHV and LHV is simply whether you assume that water vapor is condensed and the latent heat captured. The hydrogen molecule has not changed. The chemical bonds have not changed. The reaction enthalpy has not changed. What changes is whether your system design can recover the condensation heat. In condensing boilers or certain controlled combustion systems, that latent heat may indeed be partially recoverable. In most industrial furnaces, kilns, and open combustion systems, it is not. Now, this may seem like a minor thermodynamic detail, but this is where the 15% efficiency difference begins. Let's move to Image 2. Imagine a PEM electrolyzer consuming 55 kilowatt hours of electricity to produce 1 kilogram of hydrogen. That is a realistic modern number at system level. If we calculate efficiency on an HHV basis, we divide the HHV energy content of hydrogen, which is 39.4 kilowatt hours per kilogram, by the electrical input of 55 kilowatt hours. That yields 71.6% efficiency. Now calculate efficiency on an LHV basis. Divide 33.3 kilowatt hours per kilogram by the same 55 kilowatt hours of input. That yields 60.5% efficiency. The electrolyzer has not changed. The stack voltage is identical. The current density is identical. The balance of plant losses are identical. The hydrogen production rate is identical. Only the numerator in the efficiency equation changed. And that single change creates a 15.4% difference in reported efficiency. This is the trick. It is not manipulation. It is not fraud. Both values are technically correct. But if two companies report efficiency on different heating value bases without stating it clearly, the comparison becomes meaningless. In investor decks, this can subtly shape perception. A 72% efficient electrolyzer appears significantly more advanced than a 60% efficient one. But if one is reported on HHV and the other on LHV, they could be the same machine. Now let's move from efficiency to money. Look at Image 3. Suppose hydrogen sells for $3 per kilogram. That price per kilogram seems straightforward, but many energy contracts are structured per megawatt hour of energy content, not per kilogram. If we convert $3 per kilogram into dollars per megawatt hour on an HHV basis, we divide $3 by 39.4 kilowatt hours. That gives us $76.14 per megawatt hour. If we convert the same $3 per kilogram on an LHV basis, we divide $3 by 33.3 kilowatt hours. That gives us $90.09 per megawatt hour. The same hydrogen now appears nearly 18% more expensive simply because we changed the heating value basis. This difference has real commercial implications. Hydrogen offtake agreements have experienced disputes when heating value basis was not explicitly defined. If a contract specifies dollars per megawatt hour, but does not define whether that is HHV or LHV, the revenue calculations change materially. In large-scale hydrogen projects where annual volumes reach hundreds of thousands of tons, even small percentage ambiguities translate into millions of dollars over contract lifetimes. Now let's take this into heavy industry. Move to image 4. Consider a steel manufacturer evaluating hydrogen to replace natural gas in direct reduced iron production. The DRI process requires approximately 11 gigajoules of thermal energy per ton of steel on an LHV basis. Convert that to megajoules and you get 11,000 megajoules. Hydrogen's LHV is 120 megajoules per kilogram. Divide 11,000 by 120 and you get 91.7 kilograms of hydrogen per ton of steel. If hydrogen costs $3.50 per kilogram, the fuel cost per ton of steel becomes $320.95. Now compare that to natural gas at $10 per gigajoule. 11 gigajoules would cost $110. That creates a cost gap of $210.95 per ton of steel. If producing 1 ton of steel via DRI emits approximately 1.8 tons of CO2, we can divide 210.95 by 1.8 to find the implied carbon price required to equalize costs. That number is approximately $117 per ton CO2. That is the benchmark. Hydrogen steel becomes competitive at current natural gas prices when either hydrogen falls toward roughly $1.70 per kilogram, or carbon prices rise above about $117 per ton. Notice how heating value basis affects this calculation. If we mistakenly used HHV for hydrogen, but LHV for natural gas, or vice versa, we would distort the cost comparison. This is why consistent heating value basis is critical in techno-economic modeling. Now let's move into transportation. Look at image 5. A fuel cell vehicle might travel 100 kilometers per kilogram of hydrogen. 1 kilogram contains 120 megajoules on an LHV basis. Gasoline contains about 32.4 megajoules per liter. Divide 120 by 32.4 and you get 3.7 liters gasoline equivalent. So that vehicle effectively consumes 3.7 liters per 100 kilometers, which translates to approximately 63.6 miles per gallon. A typical gasoline vehicle consumes between 8 and 10 liters per 100 kilometers. Battery electric vehicles consume about 15 to 20 kilowatt hours per 100 kilometers. That corresponds to roughly 1.8 liters gasoline equivalent. So fuel cell vehicles are significantly more efficient than gasoline vehicles, but less efficient than battery electric vehicles when accounting for upstream electrolysis losses. Again, heating value basis matters. Vehicle fuel economy comparisons typically use LHV because internal combustion engines and fuel cells do not condense exhaust water vapor to recover latent heat. Finally, let's bring everything together. Look at image 6. The approximately 15% efficiency difference between HHV and LHV reporting is not technological progress. It is a thermodynamic accounting choice. HHV aligns with enthalpy of formation and is often used in electrolysis energy balance calculations. LHV aligns with real-world combustion systems where latent heat is not recovered. Neither basis is inherently wrong. The problem arises when comparisons are made across inconsistent bases. Efficiency claims become distorted, price comparisons become misleading. Industrial fuel switching analyses become inaccurate. Carbon price benchmarks become unreliable. Contracts become ambiguous. For engineering calculations, HHV should be used unless explicitly stated otherwise, because it aligns with thermodynamic definitions and simplifies electrolyzer energy balance modeling. But when you evaluate hydrogen projects, compare technologies, or analyze economics, always ask one question first. Is this reported on an HHV or LHV basis? Because sometimes the difference between a breakthrough and an average system is not innovation. It's 21.8 megajoules of accounting. And that accounting difference is about 15%. Now you know the trick.